I'm Peter Doherty. I'm the patron and namesake of the Doherty Institute for Infection and Immunity. I've been working on viruses and infection for more than 55 years, so I think I know a bit about it, but it's very complicated, and this COVID virus is a new virus, and it's a virus that continues to surprise us, so there's a lot we don't know. But I can tell you some basic principles about the infection that we do understand. And this has been an evolving understanding. We didn't understand this all at the beginning. We thought this is maybe like a really bad flu, but we know this is very different from flu for various reasons, and I'll tell you what they are. So basically the story, okay, a virus is just an inert particle. It's a tiny little thing, really minute, and you have to have an electron microscope to see it. You can't see it down a normal microscope. And basically it's basically a bit of genetic material that codes for replicating the virus, because all viruses want to do is multiply up and transmit and infect more and more people. That's all they're about. They don't want to make us sick. They don't care if they make us sick or they don't make us sick. All they want to do is infect and transmit and survive in nature. That's their whole evolutionary profile. So basically, it's a bit of genetic material surrounded by a bit of lipid, fat, and protein, and a bit of sugar on the surface as well. And so can't move itself around. Bacteria can move themselves around. They're cells. Viruses aren't. They're subcellular. So it comes in the air, or maybe we can get it to our face through hand-face contact, but pretty much it's through the air that's really we're worried about. And it comes into our nose because it's in the air. And your chance of being infected really depends on how many virus particles there are out there, which is really how many infected people there are, and how close you are to them, and how much the air is turning over. Much less chance of being infected if you're standing outside and it's windy, as long as you're standing on the wrong side, the right side of an infected person, that is the wind blowing away from them. So basically, in the air, gets into our nose. Now, what does it do? It can't do anything. It can't move itself. It's going to be taken up in what we call the mucus in the nose, the stuff that we blow out of our nose as snot. It's going to be in that, and it's got to get through that to get to the cells underneath, the epithelial cells in the nose that line the nose, and infect them. And the way it infects is that the virus binds by that spike protein on its surface, which has what we call a receptor binding domain, RBD, that binds to a molecule called ACE2, which is a normal molecule on the surface of many, many, many of our cells. And binding to that allows the virus to get into the cell. And once it's in the cell, then it gets rid of its lipid and its protein coat, and the genetic material comes out, and it will make what we call a messenger RNA, and that messenger RNA will start to make proteins and all the stuff we need to make a new virus particle. In fact, one virus particle may get into a cell. The cell then may make 100,000 virus particles. Not all of them are going to be infectious, but some of them will be. And then they have to get out of the cell to infect other people. So that's the scene. Gets into your nose, gets into a cell just by bumping into it, really. It's not moving, it's got no motor to take it to the cell. Now, when we talk about vaccine protection, what we're asking for a vaccine that we give in the arm, if we're asking for total protection up here, we're asking the antibody molecules, the ones that go around our body in the blood and can bind hold of that spike and block that receptor binding domain and block the virus from getting into the cell. What we're asking is there's enough antibody molecules up there in the nose to run in, because they're in it too, they've got nothing moving them around, to run into the virus particle before the virus particle runs into the cell. And it's pretty hard to keep a lot of antibody up there when you're given a vaccine here. If we gave the vaccine here, it might work a lot better. And people are working on, for instance, the idea of a puffer vaccine that might be used as a booster for this vaccine, might get more immunity up here. But that's not there yet. We don't have it. So you will hear that vaccinated people are being infected with the Delta variant. And that's why. It's getting into their nose. It simply hits the cell before it gets hit by an antibody molecule, just probability, and basically we can get infected. And vaccinated people can produce a lot of virus up there. They'll get rid of it quicker because we'll get, as the virus does damage, because it kills cells. It kills cells. As it does damage, we'll get more antibody leaking into the nose, so that'll affect any virus that's released and limited infecting other cells, and it will take that out better. And we'll also get the killer T cells, the ones that take out the virus-infected cell by recognizing cells infected with virus and killing it. These are the hitmen of the immune system, the stuff I worked on to get a Nobel Prize years back. So immunity will cut in quicker in the nose, but it won't necessarily protect us totally. So don't be despairing that the vaccines don't stop all infection. There's going to be infection, there's going to be some transmission from vaccinated people, hopefully less, but we don't really have very good data on that at all. It's quite hard actually to get really solid information on this stuff, even though so many people have been infected and so much work has already been done. The Delta variant's changed a lot of things. It grows a lot faster. That's all it does. It just grows faster. It hasn't escaped from the immune system. It's just a variant of the virus that's learned to grow faster and it's taken over. And that's why we're seeing this thing spread and why it's much more difficult because it's infecting more people. Now that's the flu-like side. With the flu-like side, the virus can get from that nose down into your lung, cause some pretty horrible damage in your lung. The people who look at it through imaging, you know, you come up to a machine and you're imaged, or you've got this thing going over you and all that stuff. They see what they call ground glass lesions. So I've got horrible damage there. And that's like somewhat like influenza in a way. So that part of it's not that different from influenza, the lung, the nose, lung, and all the rest of it. And that's problematic. But what we didn't realize at the beginning is that this virus is much worse than that. And the reason it's much worse than that is it doesn't just get into your lung and your nose. Influenza gets into your lung and nose. Very unusual to find in an influenza-infected person, even someone who's very sick. Very unusual to find any sign of the virus in the blood. It occasionally can be found, and it occurs in other species. Other species do get a bloodborne infection like birds, but we don't normally get that with influenza. But this virus, apart from causing that lung damage that you get, that can be a bit like that with influenza, it also gets into your bloodstream. And when it gets into your bloodstream, once something is in your bloodstream, you just think about this, every organ in the body is exposed to what's in the blood. The blood goes everywhere. So that virus, there's this ACE2 molecule it binds on, is also in cells in your heart, it's in cells in your blood vessel walls, in your kidneys, in your reproductive organs, whatever. It's everywhere, okay? And in your brain. So potentially, once it's in your blood, it can infect any cell that it hits. And so that's why, principally, where the protection, I think, from vaccination works. We know that the two vaccines we've got, the AstraZeneca and the Pfizer, and the Moderna when it comes online, basically, we know those two vaccines are preventing 85, 95% against hospitalization and severe disease. They won't protect anyone. People like me who are older, basically, I've had both shots of a vaccine. I'm about as protected as a 50-year-old, but I'm not as protected as a 50-year-old who's had the vaccine and would be much more protected than me. So it's not absolute. And people with immunological diseases or failing immune systems are still going to be susceptible. And there are other strategies for that. We're talking about monoclonal antibodies and so forth that I might talk about later. But that's what happens. So what happens in a vaccinated person is, I think, when that vaccine gives you antibodies, we've got loads of antibody in the blood, and it's stopping that bloodborne phase. Now, the bloodborne phase is horrible for two basic reasons. Firstly, the virus goes everywhere. We don't know a lot about the brain, but we do know people are suffering from brain fogs, but that may be a secondary effect of something else. But we do know it can go into the heart and damage the heart. We do know it can go into the kidneys. That's why diabetics are so susceptible, because their kidneys are often not in great shape. And we do know that in the blood vessel wall, that virus can cause the formation of clots, big clots, blood clots. It's what we call a coagulopathy, this disease. It's not just a respiratory pathogen, a pneumonia pathogen, it's a coagulopathy. We haven't seen a virus that works like this before, not in widespread human infection. So it causes the formation of blood clots. Now, there are two problems there. The big blood clots can give you a heart attack or a stroke because they block blood vessels. And I think where you hear that a young person has been infected, a fit young person has been infected and then suddenly died acutely, probably due to a heart attack or a stroke. Now, and of course, stroke, if you survive it, can leave long-term damage, as does heart attack. So this is one of the sources of long-term damage, what we can think of as post-COVID. But the other thing that does is it makes really little tiny microclots, tiny, tiny little clots. They look, if you look at the blood vessels that are supplying the lung where the oxygen exchange occurs, you can look in those blood vessels and you can see what looks like bunches of grapes because of these microclots. Now, what these microclots are doing is blocking the oxygen exchange. We bring in oxygen, we send out CO2. That happens in the lung at what we call the terminal alveoli of the lung. So if the blood vessels supplying those terminal alveoli, which are carrying the red blood cells, are carrying the carbon dioxide to there and taking the oxygen away, if those microclots are clogging that whole thing up, it's not working. And that's why we get anoxia. That's why people have to have oxygen, because they've got blood clots. Now, the doctors have got better at handling this. People who are hospitalized and they're really anoxic, they're not getting enough oxygen, they're giving them low-dose heparin early on to help control that blood clotting situation. And they're also giving them dexamethasone, which also controls a lot of the inflammation. So the doctors are doing a lot better with it, but it's still tough. And it's still a lot of people that are ending up in ICU and on ventilators. And so get vaccinated. And the reason to get vaccinated, to my mind, is to keep this damn thing out of your blood. You might be concerned about the vaccines. You may be concerned about putting something foreign into you. Well, for a start, what's being put into you in a vaccine is much less foreign than what you're getting from a chemical drug. And you're probably taking a lot more of that, actually, than you're getting in the vaccine. And the second thing is, don't obsess about the vaccine and long-term problems or stuff that you may think it will cause, and we have no evidence it does. Obsess about the long-term problems we know this virus is causing and will cause. The virus is infinitely worse than anything you could envisage happening as a consequence of vaccination, except that horrible blood clotting thing that you're well aware of, that's been widely publicized with the AstraZeneca vaccine. So that we're aware of. The authorities have been very open about risk and the risk factors, and the doctors are now much better at treating that. But don't obsess about the vaccine, obsess about the virus. That's what obsesses me, the virus. I want to keep this thing out of my blood at all costs because it may well kill me. And so that's how to look at this infection.